Okay, this is 12.2C, week's requirements for Alex. Here, if you want to graph this function, change it to exponential. Now I found its inverse. These two are inverses. And I graphed the inverse equation, or the basic equation, I should say. This is the basic equation, then that is the log equation, or the inverse equation that we need to graph. From here, we get these point values when we substitute in 2 to the x. Okay, if 2 to the negative third is 1/8, 2 to the negative second is 1/4, 2 to the negative first is 1/2, 0 is 1, 1 is 2, 2 is 4, 3 is 8. We interchange each of these values for our logarithmic inverse. Okay, so now all we have to do is graph this inverse, and that's much easier than calculating it using the logarithm or the inverse equation to start with. Okay, another one. This time I've got a little nastier base. So I change this. I go through the steps, okay, to change this to that. Because originally this would become 1/4 to the y equals x, okay? And here is the inverse of that. So based on this inverse, where we interchange the x's and the y's, then I can find these values quite easily. Okay, if this is -3, 4 to the third is 64. So this will become positive 64 over 1 here to the negative second. Then it would flip and we would get 4 to the second, or -2 to the, 4 to the negative second, or positive second would be 16. Okay, in this case, we replace -1 over there, so that flips this to be 4 over 1. And so I get 4. And then here, if it's 0, anything to the 0 power is 1. Anything to the first power is itself. Second power is 1/16, 1/64. Now then, all we have to do is interchange each of these in order to get our graph points for the logarithm. Okay, here are our graph points for the logarithm, and there in turn is the graph. Notice that we have an asymptote at x equals 0, or in other words, the y-axis. Okay, what about this one? Now, something important to notice. We're going to shift left 3 places. That creates at -3 a vertical asymptote. Okay? That creates a vertical asymptote on this problem, which will affect our range. So the domain in this case, is it -3 not inclusive to infinity? The range is from -infinity to +infinity. Okay? And where is this vertical asymptote? At the equation x equals -3. Okay, this time there's no modifier. So my vertical asymptote is naturally the y-axis. There is a negative out front. That's why this thing is going in a decaying direction rather than a growth direction. In other words, it flows across the x-axis. In this case, the domain with that asymptote here at x equals 0 is from 0 to infinity. The range, infinity to infinity. And then the asymptote is the y-axis, as I said earlier. Now, what about log of this equation? Well, this equation factors. This equation factors into that. That creates two asymptotes. It creates an asymptote at positive 4. And it also creates an asymptote over here at negative 1. Notice that my scale is by 2s. So in this case, I'm going to have a union because I've got gaps on my domain. So I have these two vertical asymptotes. Now they've drawn them in. These create boundary points for you. Areas that can and cannot be counted. So the domain in this case, here at infinity, negative infinity, because the domain is left to right, out here at infinity to negative 1. Then we've got a gap, or a union gap. And then we go from 4 to positive infinity in this direction. Again, non-inclusive on this negative 1 and 4. What about the range? Well, these both go to negative infinity, and they both go to positive infinity. Okay, we've seen this before, growth rate, decline rate. Here are logarithmic functions. If you notice, this one and that one reflect across that 45-degree angle, if we were to overlay those. Now, once again, this is repeating. When you compare exponential and logarithmic, the domain and the ranges will switch. If you have a horizontal asymptote, it will become a vertical asymptote for the inverse or the logarithmic. Okay? This one will always pass through 1, 0, 0, 1 unless there's a modifier. So that one will always pass through 1, 0. Okay? What this is saying is it can be increasing or it can be decreasing in these cases. This represents a fraction causing the decrease. That represents a positive number for the increase. Okay, let's talk about the properties of these. Okay, we've talked about these properties before already. Okay, anything to the 0 power is 1, and here's exponential form. Anything to the first power is itself. In this case, we take the 1 from here, and we've got P. Technically, we bring P out front first. Here, once again, we have a B of B equals whatever the value is. So this becomes a 1, leaving the answer of X. These two are corresponding properties. Now, what we're getting into now is what we call and contraction of logarithmic values. Okay, the first one is the multiplication rule. If you look at this, if you recall, okay, here is our argument. And what we're doing here is we've got this to the x power, and then we've got plus y power. This is a direct relationship. I had a to the m n power, that would be a to m plus n power. Direct correlation there. In the case of division, is if I had a to the m over a to the n, that this is equal to a to the m minus n power. So that's a corresponding our comparison. This is the power rule. Notice this exponent right here comes out front of the logarithm. And then you deal with whatever this is times that exponential value. Okay. This is one of the sheets in your handout packet. It basically is a restatement of those rules. Okay, here are standard exponents. Here are standard exponents. Here are the logarithmic equivalences of those. Okay. Now, if we want to expand this, in this particular case, we got three factors multiplied together. So we have log of 2 plus log of x plus log of y. Okay. Now, we're not done. All right, this is a different problem. This time, instead of having base 10, we have base 2. That's going to create an extra step for us. In this case, we do it so far just like that, except we're carrying the base 2. But what is a 2 of 2? The 2 of 2 is equal to 1. So here would be your answer on this one. Okay, here we've got this. Probably the easiest thing would be to distribute it or not. But anyway, we've got natural log 3 plus the log of this parentheses. Now, we can't break this down because those are not times. So in this case, that's as far as we can go. What about this one? This one is a quotient or a division. So we're going to subtract the logs. We have log of z minus log of 49, log base 7 of 49. But you know what? We can compute 7 of 49 because 7 to the second power is 49. So that's equal to 2. So this becomes log 7 of z minus 2. Now, anytime you've got a division one, if you have a numerator term, they didn't show it up here, but there is a hidden plus in front of any numerator term. And there's going to be a hidden, and then there will be a visible minus in front of any denominator term, unless it's already shown. Okay, log 7 of a over 14. So we have log 7 of a minus log 7 of 14. And we can, in this case, is 14. Is there anything that 7 can be raised to the power of 14? Well, no. In that case, we're done. What about this one? Here's my log of 100. And then these are a plus, so I've got to treat them like they have a parentheses here. minus log of x plus y. We can't do anything more with. Oh, actually, we can do more with this, because this is a hidden log 10. So 10 of 100 gives you a second power. So this front part is equal to 2 minus the back part. Here we have log e. This is the same thing as log base e of x to the fifth. We would bring the power out if it were in this form, wouldn't we? Well, we do in both ways, because ln of x means log base e of x, or whatever. So anyway, we take that power out front, and then there's nothing more we can do in this particular case. Okay, now we have an ln of e. Well, that secretly means, and they didn't put it in here, this. So we're going to bring the 5 out front. And what is this e of e going to give me? That means this has to be equal to 1. So my final answer then is 5. Okay, what about this one? I need to change this to a fractional radical. So in that format. Remember, this is a hidden base 10 here. Anyway, I bring the 2/3 out front, like that. And in this case, that's as far as I can take it. They use these to simplify this. What we're doing now is, this is an expanded one. They're wanting us to contract now. You've got the same base, so we can work with these. So we can pull this 8 and 1 back as multiples, but ultimately, what I just said is we could make this log 8 of 8 times 1, okay? Well, which would give me an answer of 1. But the way they did that is they evaluated this e of e right here is 1. And then they said, anything of the first power, 1 is the answer of anything to the 0 power, so this was equal to 0. So you got 1 plus 0, and ultimately 1 that way. 2 different ways you can work the same problem. Okay, we're going to expand this one. We've got 2 positive terms and 1 negative term. Okay, we've got a positive log 3 of 5. We've got a positive log 3 of z. And we've got a negative or minus log 3 of w. We need to go back and review these and see if any of them can be simplified, and they cannot. So that would be your final answer on this problem. This one, we've got 2 positives and 2 negatives. We got a positive 7 of A, a 7 of C, then a minus 7 of 5, and a minus 7 of D. In this case, we got a positive ln of x squared and a positive ln of y, but this x squared, we need to bring the 2 out front, like this, so this would be your answer on that problem. This one gets pretty involved. We better change this to a 2/3 rather than a radical. So we've got this. Now, we've got this x to the 2/3, there by numerator, and then we've got this combined y plus w plus z for the denominator. This can be further simplified. Bring the 2/3 out front, and then you've got this, and that would be your answer on this problem. Here, once again, we need to get rid of that radical, change it into 1/2 power. Okay? So the first thing we're going to do is we're going to bring this half out front, right here. All of this still remains the same for the moment. Now we're going to start working on that stuff. This 1/2 is going to be times everything that follows. So that's why I have the brackets here. Okay, first I've got log base 2 of 4 plus, because it's numerator, log base 2 of x minus log base 2 of y minus log base 2 of x cubed. I've got to bring this 3 forward. So I now have this, okay, and I can distribute this 1/2 to each individual term. Oh, by the way, 2 of 4 is just 2, okay? So what's happening here, this 1/2 times that 2 is where this 1 comes from. This 1/2 times this here, the 1/2 times this, and the 1/2 times that. Now they're wanting us to expand this. So the first thing we do is the numerator minus the denominator. Now, for the numerator, we break it down into log 3 of x plus the log 3 of y cubed. And then we've still got this denominator. First term remains the same. We bring the 3 out front. We bring the 2 out front. Okay, and that would be that one. On this one, we can break it down into the numerator minus the denominator. Now we convert the radical to a 1/2 power. In this case, we bring the 1/2 out front. We cannot multiply those because that's an addition. Where did this 1 come from? Log base 10 of 10. Here, we change this to a 1/5 power to get rid of that radical. We bring the 1/5 out front. Okay, we're continuing. Now we're going to take the log b of x to the 4th minus the log b of xy of yz cubed. Now this one, we can do this distribution. You can do it this way. You also can do this step another way. Equals 1/5 times log b x to the 4th in this case, minus, because both of they're grouping these. I don't encourage that. I would more encourage you to go straight to minus log b of y, and because that one is also in the denominator, minus log b of z. That's a z. Now that's what I would encourage you to do rather than this. In this case, you're going to have to distribute that to both places, and we'll end up with this ultimately anyway. So let's continue on. You can see they now have the same thing I wrote up here. We got to bring this 4 forward. We got to bring that 3 forward. Like so. And now we need to distribute that 1/5. This one here, you got the log of 64, you got the log of x squared, you got the log 8 of y, minus log of 3, minus log of z, minus the log of w cubed. Now we got to bring these powers forward, and this one we can change to 2. This is equal to 2 because 8 to the power of 2 is 64. So here is the 2. Okay, we brought this 2 forward. We brought this 3 forward. No, that is the argument. We brought this 3 forward. Okay. And we already talked about change of base, so I'm not going to go over that again right now. So that concludes this lesson that we have tonight to complete the objectives for week 12.